Okay, in today's class, we'll see about this controller strategies for distillation column and heat exchanger. That is what is the syllabus in fifth unit. Or is in the fifth unit. From the fifth unit, we have seen the topics like this cascade control and feed forward control in the last class. In today's class, we are seeing the next topic, which is uh, this controller strategies for heat exchangers and distillation columns. So the ரெண்டு டாபிக் வந்து these are all there for the test 3. For the test 3, to say about the syllabus, starting from of course route stability also will include, because route stability we could do with that kind of that in this test 3. So test 3 la we'll have is advanced aspects of route rate stability check, followed by this frequency response analysis, in which we have seen about Bode plots, Bode stability criteria, Nyquist plot and Nyquist stability criteria, and of course we are also supposed to see what is called as root locus plot. So root locus plot, I will prepare something, and maybe after the test we'll see that aspect. So test ku appuram at least one class, one class is enough to give an introduction about this root locus plot and any other topic which are the leftover, and we'll give an overall idea of the course. Okay. So okay, to again see the syllabus what we have seen so far in the fifth unit. We have seen about introduction to the advanced control schemes, which is cascade and feed forward control. This Smith predictor we won't touch. Let us leave that, because which is about that is how to cope up with this dead time systems. Okay, maybe we'll see after the test. Test along with this root locus plot, we'll see that. For these two topics, I will prepare material, which is root locus plot and Smith predictor, and also some idea about this model for reactor and distillation column. So these 3-4 topics are available, still yet to be discussed, which is. But whatever is left out, we'll give only an this introduction. We cannot have a rigorous approach. One class or introduction. That means the questions also will be very minimum from that topics. Okay, for the end semester at least, I can say because we are only asked to set the question paper. So at least on the topics, I will reduce questions. That is from the topics like this mathematical model for reactor and distillation column, root locus plot, and Smith predictor, and computer control of chemical processes. So these topics I can given just an idea about the topics, and we won't have a rigorous discussion. Of course, it is also not needed. And to say for the examination, I will reduce, or I will have very minimum questions on that topic. Okay. Okay, coming to today's discussion about ஒரு 14 பேர் இருக்கீங்க. Good. Let me see who are all available still. Available. Louis, yeah, right. Okay, but next class test test kind of portion. Okay. Okay, those who are coming late, they can join. Let us not wait for them. So in today's class, we are going to discuss about control of distillation towers and heat exchangers. Okay, this is the topic. I hope my screen is visible. Already I have put the screen into sharing. Okay, screen sharing is available. First, we'll see about this control of heat exchangers. We are going to see about the control strategies. What is a controlled variable and what is a manipulated variable. So these are all the topics we are going to see, and what is a controller scheme, like whether how to implement this feedback control or cascade control or feed forward control for the heat exchanger control and the distillation column control. Of course, these are the most common equipments in chemical industry. That's why we are having these topics in the syllabus. Okay. we are going to see what is a controlled variable, what is a manipulated variable, and what are the disturbances affecting the process. Okay, in the case of heat exchanger, what we are interested in controlling the process fluid temperature. So this, say that there will be a process fluid and there will be a heating fluid or cooling fluid. Okay, so normally we are interested in controlling the outlet temperature of the process fluid. So otherwise, this is a variable of importance. So for that, of course, what is the manipulation we'll have? We'll be adjusting the coolant or the heating fluid. The heating fluid most of the time it will be simply a steam, or sometimes even a hot water or any heat transfer fluids. So mostly it is steam flow. Okay, that is a fluid we are going to manipulate. So most of the time the manipulation is through a manipulating a flow of a coolant or a heating fluid. Okay, in this case we are having the steam for the heating. So we are going to adjust the steam inflow. So we can have this measurement. This F2 refers to the measurement of flow. No, F refers to flow, T refers to temperature, C refers to composition, P refers to pressure. That way, these are all the simple terminology. Okay. So we can have the measurement of the flow of the fluid entering the measurement of process flow and measurement of process temperature. Okay, there is a controlled variable, or the variable of importance is controlled variable or the process variable is the T1, which is the process fluid outlet temperature, and the manipulated variable here is the steam flow, which is say F2. F2 is the steam flow. We are adjusting by the way of this varying the control valve opening. Okay, that way we are going to do the manipulation. And disturbances entering the process could be say what are the disturbances? Say the feed flow can change, which means F1 can change, and even T1 can change, and even what else could change? This inlet pressure in the case of any gaseous fluid. So the inlet pressure can change, and even the ambient temperature may also affect the process. In what way? So this ambient is also responsible for cooling or heating of the process fluid. Though steam is the fluid used for the process, even the exchanger, many of the parts are exposed to the atmosphere. So the ambient ambient also has a role to play, but its effects are very minimum. Okay, so in that way you can at least list out what is the process variable or what is the output variable of importance, or what is called as a controlled variable. These are all the terminology for the referring to the same thing: controlled variable, or this process variable, or the output variable of importance. And the manipulated variable, mostly it's a fluid flow variable, the steam flow here. The disturbances here are the fluid inlet temperature, fluid flow rate, or even the ambient. So ambient temperature you can always take for granted for almost all of the process, no? Except for a highly adiabatic system. Okay, that effect may not be there. Okay, so these are all there, and yeah, the disturbances, no, changes in the process flow, change in the process fluid temperature, even the steam pressure will also is also a say we are measuring the flow and are adjusting the flow, but if it is the steam pressure is not constant, then it is also a variable affecting the process. Otherwise, it is also a disturbance. Okay, so otherwise these are all the disturbances, and the control objective is to maintain the process fluid at the desired temperature. Okay, by manipulating the steam flow rate. This is okay. How do we implement the control schemes? So far we have discussed the variables. And now about the control schemes. The most common control strategy is feedback control. So what sort of control here can you identify? Maybe in the question I can ask. I can give you a diagram, and what is the control strategy implemented here? So that it is a feedback, feed forward, or cascade. We can easily say that it's only feedback control. Why not it is feed forward control? Can any of you answer this question? Feed forward means, say, we know the measurement of all the disturbances. At least the major disturbance is the process fluid inlet temperature or process fluid inlet flow rate. We can measure the inlet temperature or the flow and accordingly adjust the steam input. So otherwise we should know, of course, the desired objective is to maintain the outlet temperature of the process. But instead of making this outlet temperature measurement and adjusting the steam flow, there is a useful feedback control. Suppose you measure this feed inlet temperature or the feed inlet flow rate and accordingly adjust the steam flow rate, which is a feed forward. In what sense? Otherwise, we have the perfect model of how the inflow temperature or how the inflow flow rate affects the outlet temperature. That model is known to us. So otherwise, this feed forward control is applicable only when you have a very good model about the process. Otherwise, you have a very good model about the nature of the disturbance, or is how the disturbance is affecting the output. That model is, if it is perfectly available to you, then we can implement feed forward control. Of course, on the kind of loop la. So what is available is a feedback control. Okay, we have a temperature measurement, and we have a temperature controller for which we have a temperature set point, and we are adjusting the steam flow. Fine, this is feedback, the simplest control strategy. And normally most of the chemical chemical processes are normally having a cascade loop. So cascade loop that we have discussed in the last class, the cascade loop will have a inner loop which is a very faster acting loop. So the most common fast acting loop is the flow measurement and flow control. No, flow measurement, you can have this mass flow meter or even the Venturi or this RFS device. The flow measurement is very fast, and flow control is also very fast, because the time constant, time constant is simply the volume by volumetric flow rate. There is a time constant for the flow system. Whereas in the case of the thermal system, what is the time constant? It is the heat transfer capacity, mcp by HA, heat transfer capacity into heat transfer capacity by resistance. Capacity into resistance. Capacitance into resistance is the time constant for the first order system. So most of the chemical systems are first order, and this time constant for the thermal system is, say, mcp into 1 by HA. Okay, that time constant is normally of the time constant will have a higher value in comparison to this volume by volumetric flow rate. So otherwise, these flow systems are very fast. So we'll use these flow systems in the inner loop. Inner loop is also called as a secondary or a slave loop. Slave or the primary. The primary is the outer loop. Inner is the slave control or the secondary loop. So the secondary to the secondary loop, the set point is given by the primary controller's output. So what is the primary control? Primary control is controlling the temperature. We have a measurement, and that is going to the temperature controller, for which there is a set point given. Most of the time set point won't be changed. Okay, we want to keep the system at constant irrespective of any disturbances entering. Okay, now so this set the temperature controller output is now given to the flow controller. Setting for the flow controller is coming from temperature controller's output. Okay, so for which there is a measurement, and there is a controller action, and it is acting on the final control element. So in the cascade control, again, to recollect what we have discussed in the last class, there is only one manipulator variable, and there are many measurements and many controls. Okay, one set point, one manipulation, and one output, but many measurements and many controls. We can normally 2 measurements and 2 controllers. Even there can be one more inner loop as well. Okay, normally the innermost loop is a flow loop, which is the faster response, highly responding or is fast response system. Okay, see, this is about implementing feed forward. This also I have discussed in the previous just we have discussed. No, the feed forward is about measuring the feed temperature. Not only the flow, you can also measure this temperature. Of course, okay, there are two measurements going to a same controller. Of course, you can have measurement of temperature, and for that you can give a set point. And additionally, you can measure the flow. That can be the inner loop, and innermost loop can be the manipulator variables. Always measuring the steam flow and also adjusting the valve opening. So here, of course, it is feed forward and cascade. There are both are here. Otherwise, in the feed forward also you can have a cascade. Okay, that is the idea. Okay, unlike feedback. Okay, these are all some idea about that. We can have all the combinations like feedback, feed forward, and cascade. We need not limit to a simple feedback control alone. So there are advantages with every form of every controller strategy. No, feed forward will not wait for the this effect to appear late. There is a fluid entering, and only after the change is detected by the this final measurement, then only you will act on the control valve. Whereas with feed forward, we are measuring the disturbance, and accordingly we are taking action. Otherwise, which is very fast. Otherwise, here we need not wait for the response to reach this output. Otherwise, otherwise the feed forward is actually taking a preventive action. Kind of taking preventive action. Otherwise, in terms of நம்ம பசங்க வளர்க்குறாங்க இல்லையா, parenting of a child, no, this parenting of a child, the uneducated people normally make this feedback strategy. Feedback strategy, that is, they will allow the boys to do on their own, and if they are not doing well based on the say semester marks or based on the test marks, they will ask their kids to study. Whereas in terms of educated parent, they will keep on monitor the child, and action is taken in advance. Like feed forward control, நீங்க என்ன பண்ணலாம்னா, நீங்க இந்த educated parent rearing their child, but we cannot easily match with that. At least we can have some kind of இது மாதிரி கொஞ்சம் மேட்ச் பண்ணிக்கலாம். Feedback வந்து it's a better way. Otherwise, without having any idea about the process, we can still take control. But sometimes it may be a late control. Okay. And feed forward, slightly forward, but we need to have a very perfect model of the process. And cascade, having one more control, one more measurement and control. Okay, and innermost and outermost. So cascade control gave an analogy. So the what is it? Delegating the jobs. Otherwise, job you'll ask your people to do the work. ஸோ சம்டைம் நீங்கள் லேப் ரெக்கார்ட்லாம் பண்ணுறீங்க இல்லையா, அப்படி தான் பண்ணுவீங்க. ஸோ லேப் ரெக்கார்டு என்ன பண்ணுறோம், உங்களுக்கு நாங்கள் லேப் ரெக்கார்டு எழுத சொன்னீங்கன்னா, நீங்கள் யூ லாஸ்க் some of your friends or some of your even your you may be asking your parents also to draw the record diagrams. அதெல்லாம் பண்ணிருக்கீங்களாப்பா? நிறைய பேர், even I am seeing that thing happening in my home also. Of course, I am not helping my boy, but my wife used to help my boy. Okay, these are all happening because sometime at the last moment we cannot make into we cannot create pressure, and okay, these are all the things happening. Otherwise, delegating, no, otherwise by putting inner loops is kind of delegation. Otherwise, cascade control on the never you can consider like delegating the job to your subordinates, and the subordinate has to do the job in a faster way. Then only the delegation will be perfect. Okay, good. Simple thanappa. Feedback, feed forward, and cascade. இந்த மூணு தான் நம்ம உருப்படியான இது controller strategy, most common control strategy. Otherwise, as such is simplest thing is feedback control, and better control is feed forward. But feed forward, if some unmeasured disturbance is entering, we don't have the idea of that thing. We don't have idea of that process affecting the overall system. So we also need to have a feedback. Feedback always there will be a better control. So here we have a feedback control. In what way? We are measuring the process outlet, and there is a temperature controller, and which is acting on the control valve. Feedback. And feed forward, we are measuring the flow and temperature, which is going to the temperature controller, and for which, of course, there is a combined effect which is going to the flow controller. So the flow controller is actually the secondary controller, which is actually the innermost loop. Okay. Okay, these are all taken from the site controlengineering.com. Yeah, about 35 students are available. Good. Regular student irkara. So I'm looking for some students. Okay. Prithvi nare class la kanamappa irkara. Okay. No problem. Okay. Of course. Class urgent. You can listen to the recordings later also. Of course, the last class or recording I made to upload. Today I will do that. Okay, now next thing is controlling. The next one, which is distillation column. Yeah. Okay, இது வரைக்கும் புரிஞ்சிருக்கும்னு நினைக்கிறேன். இது ரெஸ்பான்ஸ் இல்லாம இருக்கு. Okay. So next topic is controlling a distillation column. Controlling distillation column. What do you want to control in the distillation column? நீங்க மாஸ் ட்ரான்ஸ்ஃபர் இப்ப தான் படிச்சிருக்கீங்க. நல்ல டாபிக். Of course, I like this distillation. Mass transfer முக்கியமான நல்ல டாபிக் distillation. And distillation, of course, it is having the basis from your thermodynamics. Very nice topic. Of course, that will be a very useful topic. Distillation, you can operate most of the chemical engineering plants. Most of the this organic and petrochemical plants are of having distillation. Distillation is the most common operation there. Okay, yeah. Distillation what we want to control. இன்னொரு 10-20 நிமிஷம் இருக்கு. Maybe we can ask some questions also. இல்லையா, யாராவது ஆன்சர் பண்றீங்களாப்பா? What is இது வரைக்கும் கிளாஸ்ல ஒரு கிளாஸ் கூட இன்டராக்ஷன் இல்லாம போச்சு. நிறைய கிளாஸ்ல மோஸ்ட்லி I am simply delivering something. So what we are interested in controlling, what is the meaning of control of distillation column?
Sir, feed flow rate, solvent flow rate, reboiler heat.
Reboiler heat. Okay, what is the ultimate objective of a controller? Distillation column எதை கண்ட்ரோல் பண்ணுவீங்க லாஸ்டா? Okay, feed flow rate பார்க்கணும், reboiler பார்க்கணும், எல்லாம் பார்க்கணும். So what we are interested in, what is the need, what is the ultimate need for a distillation column?
Recovery
of solvent, sometimes even separation of a feed mixture. Yeah, separation of a mixture. There is purification. Yeah, that is a ultimate objective. So you will be interested in checking for the composition of the distillate, mostly the distillate, or sometimes even the this bottoms. So otherwise, composition of the distillate. Yeah, we are interested in the composition of the top product, the product of importance. That composition should be maintained constant. Of course, these are all the variables like feed flow rate, reboiler flow rate, condensing reflux rate. These are all the variables affecting the process. The ultimate objective of a distillation column is to control the top product composition. It's not the top product, sometimes even the bottom product also. Okay. So how do you control this composition? The question is answered. Distillation column படிச்சிருக்கீங்க. But already we have seen this. This composition measurement is a slow process. Yeah. How do you measure the composition? You will be able to take the sample and say the simplest way is by doing titration, or by measuring, sending that sample to a gas chromatography or liquid chromatography and finding the composition. But this and all a slow process. In what way? Because at least the time of that of about a few minutes is needed to check the composition. So how do you get the real-time measurement of the composition. Otherwise, we cannot wait this for this composition measurement. Otherwise, we can infer the composition in another way. Can any of you say the answer for this? Otherwise, instead of measuring composition, we can also check for the composition. Otherwise, check for the maintenance of the composition by the simplest measurement. What sort of simple measurement you can have? Distillation காலத்துல என்ன measurement எடுத்துக்கலாம்ப்பா? Maybe I can show you the diagram. Okay, this is a distillation column. So otherwise we are interested in getting the top product composition. This is D oda composition or sometimes the B oda composition. Distillate and bottoms. So instead of composition, what variable you can use to infer the composition, which is a fossil measurement in comparison to the composition measurement. Thermodynamics படிச்சாச்சு, அதனால you can say about the composition easily. ஒரு ரெஸ்பான்ஸ் வந்தா நல்லா இருக்கும் இல்லையா? தேங்க்ஸ் மாதேஸ்வரன், நீங்க கொடுத்த ஆன்சர் ரெலவென்ட் பட் நாட் கரெக்ட் ஒன். ஸோ நானே கொஸ்டின் கேட்கணுமா? பட் வேண்டாம் இதெல்லாம் இல்லையா? கொஸ்டின் கேட்டு நாங்கள் ஆள் லைன்ல இல்லைன்னா கஷ்டமா இருக்கும். So say you know this relationship between the temperature and composition. So the pxy txy diagram. Saridana, pxy txy diagram. Okay, I will ask another question, relevant question here, which is you have seen about isobaric and isothermal equilibrium. Which equilibrium will be maintained in this distillation column? Distillation column consists of so many trays. Idhula the pxy diagram use aguma illa txy diagram use aguma?
So
pxy means isothermal operation, yeah. So pxy diagram is
about isothermal illa sir. Isobaric pressure constant adha sir.
Okay, good. Why not isothermal? Isothermal la பண்றது என்ன பிரச்சனை?
Sir isothermal na ஒரே increasing temperature தான் சார் இருக்கும், கீழ இருந்து ஹீட் பண்ணும்போது distillation column.
Then why do we study isobaric operation? Isobaric னு போட்டு ஒரு VL எல்லாம் படிச்சோம் இல்லையா? சார் isothermal equilibrium, isothermal னு படிச்சு isothermal operation பண்ணனும்னா எப்படி பண்ணுவீங்க? Isobaric okay, I can understand. We expect the entire pressure to be uniform. Of course there will be still a pressure drop, yeah, that you cannot avoid because of flow. Fine. So how do you maintain? Suppose you want to maintain isothermal operation. Isothermal operation பண்ணா என்ன பண்ணனும்? Isobaric ங்கிறது okay, we are easy to understand because column entire pressure is of uniform and மேல இருக்கிற temperature கம்மியா இருக்கும், கீழ இருக்கிற temperature ஜாஸ்தியா இருக்கும். So the top one corresponds to the condensing conditions and bottom reboiler. So மேல வந்து light component, here the heavy component. Fine. Suppose you want to carry out this operation in isothermal manner. அப்ப என்ன பண்ணணும்? pressure எந்த மாதிரி வேரியேஷன் இருக்கும்? So for isobaric I have said about this temperature decreases from the bottom to top. Isothermal la பண்ணா என்ன பண்ணணும்? Okay, there is a difficulty with that isothermal operation. அது நீங்க மேபி உங்களோட மாஸ் ட்ரான்ஸ்ஃபர் கிளாஸ்ல நீங்க கேட்டு லாஸ்ட் கிளாஸ்ல வேணா அதை பத்தி பேசலாம். Okay, that I need not give an idea here now. அதை நீங்க ட்ரை பண்ணி பாருங்க, நானே சொல்றதுல அர்த்தம் இல்லை. There is also not relevant to my discussion. So what we are interested in, instead of measuring the composition, we can simply measure the temperature and we can
சார் நீங்க இப்ப சொன்னீங்கன்னா தெரிஞ்சு போகும் சார், அடுத்து ஒரு எஃபெக்ட் எடுக்க மாட்டாங்க சார் மாஸ்டர் சர்டிஃபிகேட்.
சரி, அதாவது எல்லாத்தையும் ஆன்சர் கொடுத்தீங்கன்னா யோசிக்கிறதுக்கே சான்ஸ் இருக்காதுப்பா.
சரி சார், ஓகே.
அதனால இன்னும் மாஸ் ட்ரான்ஸ்ஃபர் கிளாஸ் 1-2 கிளாஸ் இருக்கும், அங்கேயும் பேசினீங்கன்னா அவருக்கு சந்தோஷமா இருக்கும் இல்லையா? நான் என்கிட்ட பேசி நான் பேசி உங்களை நீங்க உங்களோட இது பண்றது நீங்க அங்கே கேட்டீங்கன்னா இன்னும் நல்லா இருக்கும் அவருக்கும். நெக்ஸ்ட் கிளாஸ்ல பேசலாம். நெக்ஸ்ட் ஒரு கிளாஸ் இருக்கு, மேபி இந்த டாபிக் ரீகலெக்ட். ஓகே, குட். சரி, temperature and you know the relation between temperature and composition. You know the what sort of diagram? TXY diagram is going to be useful here. So corresponding to, of course we know how to make this TXY diagram for a binary system, but industrial operation is not binary. You have a multi-component mixture still you can connect this temperature and composition. Yeah, thermodynamics la படிச்சிருப்பீங்க போன செமஸ்டர்ல. So TXY diagram la irundhu you can always, what is meant by TXY diagram? This T and distillate, no? Distillate is a liquid and corresponding temperature is known. So temperature and compositions are having a correlation. Okay. So simply measuring the temperature, we can take control action. Okay. So always industry la pathina enna pandranga, they are simply measuring the top product temperature, and not only top product, and they will also have measurement at some other trace as well, which is an indirect measurement of composition. Okay. Okay. So let us see the thing. So always enna pandrona, 1 minute, let us go from the first, no? So the objective is to control the composition. Okay, இதெல்லாம் நீங்க படிங்க, தேவையில்லாம பேசிட்டு இருக்காங்க. Okay, there is column pressure. There is a most commonly controlled variable. How to control the column pressure? Column pressure control பண்ணணும் இல்லையா? Because why do we need to control the column pressure? Because say if the temperature and composition have a correspondence at a given pressure. If the column pressure is not constant, then you'll be having a different correlation. You know the effect for each and every pressure there is a correspondence between T and X. So we need to suppose the design is for 1 atmosphere, you need to operate at the given pressure. But how does the pressure change? What is the most common variable affecting the column pressure? The question I can யாராவது நீங்க ட்ரை பண்ணுங்க பார்க்கலாம். So always we should control the column pressure. Column pressure means the distillation column entire pressure, but normally we'll measure the pressure at the top of the column, which is again a measure of the condenser pressure. How do you regulate the column pressure, or how do you maintain the condenser pressure? என்னப்பா பண்ணலாம்? Condenser pressure ஜாஸ்தி ஆயிட்டே போகுது. How do you reduce the pressure? The simplest question.
So gas flow rate reduce பண்ணலாமா?
That means the top vapor flow rate. Yeah, gas.
Vapor flow. Sorry, gas flow rate.
Vapor flow rate குறைக்கணும். Vapor flow rate how do you reduce? You know, say காலத்துல இருந்து மேல வந்துட்டு இருக்கு. You don't have any, you cannot operate the valve column pressure குறைச்சிங்க, அதாவது gas flow rate குறைச்சிங்கன்னா கீழே again back ஆகும் இல்லையா? Instead, what is easily achievable? Column pressure. Okay, nice point. Otherwise, we have to reduce the this vapor flow rate. So otherwise, we can think of increasing the this condenser coolant flow rate. You can increase the coolant flow rate. Coolant flow rate in the condenser ஜாஸ்தி பண்ணீங்கன்னா என்ன ஆகும்? Automatically condensation will happening at lower temperature. So that means the column pressure will reduce. Okay, the simplest way is increase the condensing fluid, or is increase the coolant to the condenser. Okay, சரிதானப்பா? Is it fine? Otherwise நான் அங்க கேக்குறேன். Fine. Otherwise we have to increase the coolant flow rate to the condenser. The cooling water, this what is it? CWS is referring to the cooling water system. So the cooling water flow rate is ஜாஸ்தி பண்ணணும் அவ்வளவுதான். So otherwise, the simplest way is they are simply adjusting the cooling medium flow variation, or there are main 3 methods: vapor flow variation, flooded condenser. Okay, the moon method. This is the cooling medium flow variation is the easiest. Simplest and direct method is cooling. Okay, I cannot read that. Later on. So we can adjust the coolant flow rate. Okay, measure the pressure and here இதில் என்ன பண்ணிருக்காங்கன்னா, which is about the accumulator the reflux accumulator is there, no? So the reflux accumulator flow to the accumulator. Okay, பெருசா இருக்கு, வேண்டாம். Service the cooling water flow rate just பண்ணணும், simplest. Okay, the other things you please go through. Or venting excess gas to the flare, but that is not a nice method, because excess gas or excess vapor. No? So that means you'll be actually wasting the product. Or sometimes pressure control using inerts. So you can even apply some inert gas over the condenser. So whenever the column pressure falls, you can admit inert gas. That way you can also pressurize the column. So column temperature control is the most popular way of controlling product composition that already we discussed. Yeah. So what we do is we measure the temperature and adjust the reflex rate. Okay, adjust the reflex rate means okay again if you increase or decrease reflexing again, it will again affect the total column, and also it will also regulate the associated the coolant flow. You can adjust this reflexing also. Likewise, the temperature control at the bottom is by adjusting the heating to the reboiler. Okay, so otherwise the most common control is simply adjusting the reflex rate and the reboiler rate. So reboiler rate is simply increasing or decreasing the opening to the reboiler, simply the heating fluid. Say most of the time it is steam or any other heat transfer fluid. So here it is simply adjusting the reflex rate. But again, column pressure control is normally by, so the column pressure control is by adjusting the what is it, the cooling water system. Okay, so the pressure control, of course temperature control is normally by the adjusting the reflex rate. But of course all the things are having in this you cannot if you say, even if you adjust the reflex rate, that will also have effect on this cooling load. Okay, if you try to change one variable, it will also affect the other variable. That should be kept in mind. Okay, let us see the controlled variables, or is the variables of importance. The distillate composition, that is of prime importance, or is a bottom composition. Sometimes either of the composition will be of important, or both will also be important. And the accumulator level, yeah, this also will be of importance, provided this this Y is again going to some sort of processing. So this level in this tank, that also be kept at some desired level. There only will be having sufficient flow for the subsequent operation. And the sump level, or is this bottommost trace level, and the column pressure. So these are all the most common controlled variables, or the output variable of importance. So the most common is pressure control and the combustion control. In addition, we have this level in the reflex drum and the level in the bottommost tray. Okay, so level in the bottommost tray is important because it's again going to affect the subsequent operation of the bottoms. And manipulated variables are the most common is the QC as well as QR. QC is the condensate heat load, and this reboiler heat load, or reboiler duty, condenser duty. These are all referring to the heating and cooling. And reflex rate, this is one of the manipulated variable. So reflex rate is normally used for controlling the temperature. And flow rate, these are also variables. This manipulator, you can even manipulate the distillate flow rate as well as bottom flow rate. That way also you can increase or decrease the reflex and reboils. And disturbances entering the process are this feed rate and feed composition, feed temperature, as well as feed quality. Q you will use for quality, yeah. And reboiler heat duty. There is S refers to steam flow rate, W refers to the cooling water flow rate. Okay, so you can use this kind of pairing. Distillate combustion, There is, if it is the controlled variable, and you can adjust the distillate flow rate, and the most common disturbance variable is the feed flow rate. And bottom composition, the bottom flow, you can adjust the bottom flow and feed composition again. Feed flow as well as bead composition, both are having the same effect. Okay. And accumulator level, that means the top reflux accumulator, which is again affected by this feed temperature, sump level, or is a bottom plate level, which is manipulated by the way of reboiler duty. And column pressure normally is manipulated by condenser duty. Okay. So the column pressure என்ன பண்ணணும்னா டாப் ப்ரெஷரை மெஷர் பண்ணிட்டு you measure adjust the cooling in the condenser. Of course, the overall column pressure பாத்தீங்கன்னா it will be from the bottom to top. Topல பாத்தீங்கன்னா pressure, there will be a pressure drop. No, there is vapor is passing from the bottom, and by the time it is reaching top, there should be a low pressure. Then only the vapor can pass from the bottom to top. Of course, the liquid is coming down. Liquid is coming down by gravity. So அதனால மேல pressure கம்மியா இருந்தாலும் again because of the added gravity, liquid will come down. So there is a slight pressure drop. Why there is a pressure drop? Because vapor has to pass through every tray. Only if there is a pressure drop, there will be a flow. No? There should be a pressure difference between the bottom and the previous top tray. Pressure drop இருந்தா தான் then ஆகும் pressure free, this vapor has to pass from the bottom to the top. So there is a pressure drop, but this pressure drop is assumed to be very minimum. That is, we are assuming the total column is of uniform pressure. Okay, this kind of control loops are here. Say another loop in Baklama, say flow control. We are measuring the flow and taking action. So this is what is called as a kind of feed forward control. And here the level control. Level control, we take a measurement of again flow. So various combinations are implemented here, and this bottom flow. சரியான diagram இல்ல இதுல. So it's like temperature control mari, the pressure control I didn't have a much good diagram. Okay, at least we can also try to implement the feedback, feed forward, and the cascade control strategy. So I will look for some figures for this feedback, feed forward, and the cascade control strategy in the distillation column. Of course, distillation காலத்துக்கும் நீங்க the heat exchanger படிச்சதே அப்படியே இங்க எழுத முடியும். So wherever there is a temperature control, how do you implement this feedback? So measure the product outlet temperature and take control on the flow rate to the heat condenser. That is a feedback control. And feed forward could be measuring the flow of this distillate and accordingly controlling the flow. So there is a feed forward control. And cascade, so normally the inner loop will be the simplest flow loop. Okay, if possible, I'll try to collect some more figures and make it here. Okay. Okay, இந்த அளவுக்கு தெரிஞ்சிட்டா போதும் இப்போதைக்கு for the test. Again, to recollect what we have seen for the test 3. Test 3 க்கு என்னென்ன டாபிக்னு ஒரு தடவை குயிக்கா பார்த்துடலாம். So the route stability oda the this advanced aspects, which is about if any of the this column element, or if the first column element is turning to 0 even before finishing the entire rows. Say for example here the 4th and 5th rows are turning to 0 for a 4th order polynomial. For the 4th order polynomial up to the 5th row you have to write. The 0 வந்துச்சு அதனால we are this also turn to 0, but you have to rearrange this route in a different form by using this wherever this s is there, change with 1 by s, and you'll be writing another polynomial and construct a route array for that polynomial and check the stability criteria for that for that rearranged polynomial. Okay. Based on that, you can say about the stability. And another thing is about the entire rows turning to 0 na enna pannom, you have to take a derivative, and derivative oda route array you have to take. No, I have given one idea, but I would 1 minute, I will look for that thing in our LMS course. I'm looking for whether the entire contents are there in the PDC course page. This thing you can go through. And the example always in a case you have to also take a derivative if all the rows are turning to 0. So then that you have to take a derivative of that previous row, and using that you have to construct a route array. Example route stability for some peculiar cases. And we have seen about frequency response kind of introduction, which is about how to get the amplitude ratio and phase angle. Amplitude ratio and phase angle are obtained by this transfer function, and replace this S with j omega, and obtain a complex number and take the absolute and argument of that complex number, and that will give you the amplitude ratio and phase angle. Okay. And how to construct the Bode plot. Bode plot is based on the asymptotic relations between asymptotic values at the low frequency and high frequency limits. So using that, you can make this Bode plots, or is simply till tau omega equal to 1, we will be having this low frequency, and after that it is high frequency asymptote. For first order, it is slope is equal to -1. For second order, slope is -2. For other systems, how the trend will look like, adhalam paathukonga. And what is Bode stability criteria, which is based on Bode stability criterion is I will take from here. So Bode stability is based on the open loop transfer function. That is for the open loop. 1 minute. You know what is a open loop? Normally there is a closed loop. You will cut a loop after this measurement. So measurement is not given to the comparator. So you have this all the elements in the loop now. So in that, for that open loop, you make the Bode plot. And if the Bode plot from the Bode plot corresponding to the corresponding to the crossover frequency. So what is crossover frequency? From the phase angle plot, we can get the crossover frequency. Crossover frequency corresponds to a phase angle of -180. So for that, you'll be getting that crossover frequency. At the crossover frequency, if the amplitude ratio is greater than 1, then the system is said to be unstable. Say for example here, the amplitude ratio for say corresponding to a KC of 20, the open loop transfer function is having a amplitude ratio which is higher than 1. So this system is unstable. And there is also related concepts like gain margin and phase margin. These are all normally used for controller settings. Yeah, normally a positive gain margin and positive phase margin are to be there. So phase margin is about this 180 minus the absolute value of the phase angle. Not the absolute value. This 180 minus this phase lag. Okay, this 5p refers to the phase lag of the system. Say phase lag is here somewhere around some 150 or so. So my 180 minus 150 will be 30 degree in this case. It's almost closer to 30 degrees. And gain margin is about the gain corresponding to a phase angle of -180. That is giving a value of phase. There is a amplitude ratio is m, and if this m is lesser than 1, then you'll be having a gain margin which is 1 by m, which is a positive quantity. Gain margin should be a positive, and phase margin is also a positive quantity. Normally, a phase margin of about 30 degrees is acceptable. 30 or minimum of 30, and gain margin somewhere around some 1.6 they are taking for that thing. Okay. And the Bode criteria is inapplicable for systems which have this kind of phase angle plot. Phase angle, if it is, so we should have a monotonously decreasing phase angle. Whereas if you have this kind of trend, or phase angle decreases and again increases for certain ranges of frequency, then this Bode criteria is not applicable. Otherwise, we'll be having two or many crossover frequencies. Say normally one crossover frequency should be there. So here we have 1, 2, and 3 crossover frequency. Crossover frequency refers to the frequency for which phase angle is minus 180. Okay. Okay. For this kind of cases, we'll go for Nyquist stability. And Nyquist stability also we have discussed. Nyquist stability. So before that, there is a topic what is called as controller tuning. Controller tuning based on this ultimate controller gain. Okay, I'll make some material for this controller tuning and make it available in the web. Okay. And Nyquist plot is again the plot of amplitude ratio and phase angle for increasing values of omega. Say for example 0 to infinity and 0 to minus infinity. We can make this plot. Of course, this is a polar plot. Bode plot to Nyquist plot is difference. This is the Bode plot is log and semi-log, and here we have simply polar plot, single polar plot, which is giving information about amplitude ratio, which is the distance from the center point, and the phase angle, which is the angle it is making with the center point. Okay. Say for example, at the start angle is 0, and at somewhere here at this point, angle will be somewhere around some 45 degree also. So likewise, we will make this variation of amplitude ratio and phase angle are marked in the same plot. Okay, இது எப்படி வருங்கிறது சின்ன ரீட் பண்ணி பார்த்துக்கோங்க. And the Nyquist stability is based on the comparison with unit circle. This in the Nyquist plot, you make a unit circle plot, and if your Nyquist plot is encircling that unit circle, then you say that the system is unstable. So இதெல்லாம் நம்ம லாஸ்ட் கிளாஸ்ல syllabus test 3 kind of portions. And the next topic is about the advanced control schemes, which is about the cascade and feed forward control. You can a qualitative treatment alone you can go through for the advanced control schemes. Then we have seen about the controller strategies for heat exchanger and distillation column. So topic கொஞ்சம் நிறைய இருக்கிற மாதிரி இருக்கு, but simpler questions only will be asked. I will also prepare some questions for you for practice, and that will be available at least இன்னொரு 2-3 நாள் அதை பண்ணி போட்டு தரேன் நான். And of course test is on. நம்ம டெஸ்ட் என்னைக்கு வருது? Okay, I will see that, no problem. ஓகேப்பா, ஓரளவுக்கு கவர் பண்ணியாச்சு. இன்னும் ஒரே ஒரு கிளாஸ்ல whatever is left out I will cover in the class. Before that, I will also prepare some material for the controller settings, and the Utpana topic I will try to give some material. Okay. So whatever best possible from my end, I will make.